The lecture I'm about to start is going to be on digital logic circuits. This is section 2.4 in the Ec book. And the main reason, I think, for introducing this particular topic is, well, A, it's actually the guts inside of computers. It's what makes computers work. So I think it's reasonable for a student of computer science to understand the inner workings of the processor. But it's also a great and very visual way to understand logic. So it has two benefits for us. So let me get started on how you think about this. I think some people will have had a circuits course, so they'll have seen similar material in the past. I just want to warn you, you have to do it kind of my way here. We're doing the math version of digital logic circuits, not the computer science version. So there are some slight differences. Well, the main thing is gates, or elements that look like this in a logic diagram. This one that looks like the letter D is the AND of its inputs. So if the inputs P and Q were there, then what comes out of this thing is P ANDed with Q. And personally, I remember this by thinking about the word AND, but spelled with a capital D on the end. It looks just like the circuit diagram. The schematic element for a circuit diagram. And then the other one is OR. I don't know if that helps. Anyway, what does the OR symbol look like? It also has two inputs. The back edge of this thing, in fact, all three edges of this little triangular-ish looking thing are curved. So it looks like that. Again, if we have P and Q as the inputs, the output on this would be P ORed with Q. I don't know, at various times I've kind of imagined this looks like a letter R a little bit. You see a letter R that's kind of, no, that's just not working. Remember, AND has the D on the end, and the AND gate looks like a D, and the OR thing is the other one. All right, if you have had circuits, you'll have seen this circuit diagram element, where you have a double line on the back of the OR gate, or a double line on the back of the AND gate, and that stands for, this one is NOR, and the other one, which looks like this, is NAND. I'm sorry, I'm bad. This is not done. This is not NOR. Darn it. Well, I messed up, but you know what? I'm fixing it fairly quickly. This circuit element is called XOR, not NOR. I don't know what I was thinking. And I guess the main reason for me messing that up is because I never use it. An XOR gate is actually much more complicated than an OR gate or an AND gate, and you can use ANDs and ORs to build an XOR. So we're not going to look at XOR. Yeah, it actually is used in some processor designs, but it's not necessary. You could always build the same thing out of ANDs and ORs, which we'll get to. The one thing that we are going to use in addition to these two, though, is a really kind of an interesting, almost magical little circuit element. It's drawn like this, and that stands for NOR. Darn it, I keep messing up today. That symbol is a negator. It negates, or some people call it an inverter, but I don't like the word inverter for this because inverters are actually devices that turn DC power into alternating circuit power. So an inverter is something that you can use to get like wall circuit juice out of a battery. Yeah, so negator is my preferred term for it. But anyway, that implements the not. If this is P on the input, it's not P on the output. Now, there's a little element in the book where they explain how you can build a circuit that that implements AND, or how you can build a circuit that implements OR. They show it with switches. It's, of course, in a real integrated circuit, the things that make up these things are transistors. But I think it's clearer if I show it to you with switches. Just think of a transistor as a switch that's powered by electricity. If you apply a little bit of juice to one of the legs of it, it turns it on or closes the switch. So let's look at those kinds of diagrams that clue us into why ANDs and ORs are so easy to build and so easy to work with. Well, yeah. Here's a very basic circuit element you run into all the time. That's a battery. It supplies power. And if I took this battery and just hooked it up to a light bulb, which I'm going to try to draw it schematically, looks like an actual light bulb. Of course, it will come on, right? So if you just, but nobody actually wants to have a light bulb that's just on all the time. So consequently, they put switches in. And a switch is drawn into the circuit by putting sort of dots there and a little slanty bar. The idea is, I mean, you know, some of the early switches literally looked like this. You'd have a bar, we'd push down on it, and it would make contact with the other end of the wire. And in fact, personally, I have made switches like this by using a little bit of bent up aluminum from an old can and make a leaf spring kind of switch. So yeah, so then of course if the switch is in the position I'm showing now, the light bulb would not be on, but if I could push it down until it made contact, then the light would come on. So what happens if you have two switches that are like this? I don't know that anybody would ever want to have you know, if I was designing a flashlight, I really wouldn't want that. I have to press this button and this button in order to get the light to come on, wouldn't I? Well, that's really the AND operation. If instead of switches, these were transistors, the inputs would be coming in and they would be making those transistors act like a closed switch if they were energized. And so, I mean, I guess I could draw it for it. Now, you can imagine it. So okay, I'm vacillating. Let me go ahead and draw what it looks like when you turn it into transistors. P and Q are your inputs. You still have the battery in there, but usually in a real computer, the battery it's not a battery, it's a power supply. So we talk about the plus 5 volt supply and then ground, which is the other end of that thing. Ground is usually drawn like this. Okay, so I'm going to turn these transistors, here's a transistor, on if, if that one will turn on if Q is on. In other words, if whatever input line Q has some juice on it, this thing will turn on. And we're going to run from the plus 5 volt to the next transistor because we're trying to emulate this same thing here. It's called a series connection between the transistors. Now I've got to go out to my light bulb and then to ground. So this is a little different because I didn't do it with a battery. We've got a plus 5 volt, we've got ground, but the basic idea here is the light bulb lights up if both P and Q are on. And I could finally turn this into the actual guts of the logic circuit. It's not really a big deal. It's just you don't really want to light up a light bulb. You want to supply some juice on that wire that comes out of there. So this is your output. There's your P and Q. This whole thing is what's inside one of those Ds. Well, I'm simplifying things slightly. There's actually other elements of the circuit, some bias diodes and a few resistors, but just for safety's sake, there's some things in there that prevent the gate from damaging itself if it's hooked up wrong. But basically, that's the idea to get an AND gate. Now how about, I won't do the transistor thing a second time, but let's think about how switches could be hooked together to produce the OR idea. I want the light bulb to come on if I push one switch or if I push the other. And if I push them both, it should come on too. Well, that's what's known as a parallel circuit. Let's see, we're going to still have our battery. But what we need for these, the two switches we're going to use is sort of parallel branches. I'm going to split it off like this and have a switch in the top half of the top branch and another switch in the bottom half of the branch. So a switch there and a switch there. Do you see that if I push the top one down, then electricity will be able to go through there and make it to the light bulb? Forget to put the glass envelope around the light bulb. And so the light bulb will turn on. If I push the lower one, it'll go down through the low one. If I push them both, it'll probably, a little bit of juice will flow through both lines, and anyway, the light bulb will light up in all three of those scenarios. We should show how engineers look at these kinds of circuits. They do it via an output table, or an input-output table. Which is going to, I think you're going to find remarkably similar to something else we've done. The inputs would be, let's call them P and Q, as I did it before on the circuit. The output, we'll just call it out. Well, I can't just call it out because I want to do the AND here. So I guess I have to write it as P and Q. Where it's different from a truth table is we don't use T's and F's here. We use ones and zeros. We use binary digits. I could call it 0 volts and 5 volts or 2.8 volts or whatever the type of circuitry we're using is. But usually there's some set voltage limit that says anything above that is on, is considered a 1, and anything below that is off, is considered a 0. So 1 1, 1 0, 0 1, 0 0. Those are the 4 possible combinations of on and off for the inputs, P and Q. And if we're implementing the AND gate, well, it only comes on if both of its inputs are on. So you get a 1 there, and you get zeros here. Really, I mean, that is exactly the same thing as the truth table for the AND operation, with 1s turned into T's, or T's turned into 1s, rather, and F's turned into 0s. It's identical. The I/O table for OR then would look like this: P, Q, P or Q, 1 1 1 0 0 1 0 0. When does OR come on? In each of the top 3 positions. When anything is on, it is on. It's only off in the one position where they're both off. I guess for completeness, I could show you the input-output table for the NOT operation, but I can't show you the diagram for it. Honestly, the circuit that makes NOT happen is beyond my capacity to understand. It's like black magic to me. The way the engineers have worked out the system to sort of bleed juice away from one transistor and make a transistor behave so that it switches the juice from one way versus the other way. It's a little bizarre. I'm just going to show you what the I/O table looks like. So if we had P and the little NOT gate symbol, so this is P on the input, it's just not P on the output. Well, you know what the output table, this is exactly like the logical table for P and not P. P and not P would be, P is either on or off, and not P does the opposite. When P is on, not P is off, and when P is off, not P is on. If any of you have a do electronics as a hobby or something, it is an interesting project to try to build yourself a NOT gate. And there's literally gazillions of them in every CPU that you've ever dealt with. But well, anyway, let me not dwell on it too much. All right. One of the things that we're going to need to do is have a specified I/O table and figure out a circuit that makes that happen. So that is, we want to be able to build a circuit that does an arbitrary I/O table. And that tells you, if you can do it, by the way, that tells you something interesting. The AND gate and the OR gate and the NOT, those three components that we're using, if they can make any circuit happen, they're complete in a certain sense. They're enough to create every output table you might ever want. There's a few sets of components that are complete. And this is why NAND and NOR come in, because it's actually possible to build every logical output possible using only NANDs or only NORs. And yet we're still not going to talk about them right away. So we want to look at building things using ANDs and ORs and NOTs without the other stuff. Well, I guess I should head this with what we're doing. We're building a circuit for an arbitrary I/O table. And we're going to do it in sort of two phases. First, we're going to talk about how to build a circuit that just recognizes a particular row in your truth table. And then once we've got circuits that do that recognize rows, well, we'll just look at what rows we want to be turned on, and we'll build a recognizer for each of them, and then we'll combine them. The way you combine them is known as disjunctive normal form. But I'll come back to that. Let's first talk about a recognizer. I like to build in a shorthand at this point for when we're doing recognizers. It's that you can take a circuit that involves three inputs, like P, Q, and R, and you want to AND them all together. That would mean you should have to build an AND gate for that one, and then take this guy plus this one's output and feed them into another AND gate, and that would be your output. Or, because the associative law is true, you could do P would be the last one, and it would be ORed with, it would be ANDed with Q and R. So since that's possible to do, and possible to do in many ways, and it's sort of immaterial what order you do them in, people have this shorthand, which is to use big AND gates that have three inputs. So instead of doing all of that, which is sort of needless, when you've got three inputs and you want them all to be ANDed together, you do this. Feed all three inputs into a giant size AND gate. A multi-input AND gate, if you like. If the inputs are P, Q, and R, then the output is P and Q and R. And I know I haven't put parentheses in, but the whole point is that you can do the parentheses any way you like. So, yeah. So if I have a multi-input AND gate, or it could just be two for certain situations, I can put NOTs in front of it and arrange for this circuit element to come on in a particular row of a truth table. Let me give you a quick example of that. Let's do it with just a two-input AND gate. Suppose I want this to be my I/O table. P and Q go 1, 0, 0, 1, 0, 0, right? But I only want the output to come on in the third row, and everywhere else I want it to be zeros. That's what I want as my output. Can we build ourselves a AND gate that will do this? It's actually not bad. You want to This is why they call it a recognizer. You want to recognize this row, which has P off and Q on. So if P is off, you want to flip its state so that it's on, and Q is on, so leave it alone, and feed those things into an AND gate. And you can almost read this by going P's off, Q's on, because this one has a NOT and this one doesn't. And then the output is going to be, well, what would the output of this be? It would be not P ANDed with Q. Which, if you think back to how we did this stuff with truth tables, that's exactly where you would get a T in the third row. Yay. Suppose I had a more ambitious thing where there was 3 variables as the input. I'm going to save some of this table because I can. How about we have, although I like to keep the variables in the order P, Q, R. So the top half of the table has all 1s in it for P, and the bottom half of the table has all 0s in it for P. And then the Q and R things have exactly the same pattern in their in the bottom half of this table as they did in the top half. And again, that's like doing the 3 input truth table with 3 predicate variables to deal with. You get all 8 possible combinations of not T's and F's anymore, but 0s and 1s. Okay, so suppose I wanted to create something that had this row. What is that? Row 5. It was a 1, and it was 0 everywhere else. Could we make a circuit that does that output? Sure we can. What we want to do is sort of make the changes so that the inputs are all 1, which means I'm going to take P and negate it, and Q and R I'm going to leave alone, and all those things are going to get fed into one of these multi-input AND gates. P, Q, R. Cool. So this is going to give us the output table we want. Great. Now, so what do you do when you have multiple spots that you want it to be on in? And instead of a single thing, multiple things. Well, let's do that for, how about just a simple example where I want that to come on as well. The reason I want to do this is I've already built half of the circuit I need. What I also need now is to recognize that row. That has 0, 1, 0, so I need not, nothing, and another not. So this would recognize the other 1. And so what we need to do is figure out how to hook those 2 recognizers together in order to get the correct output, that it comes on in either row 4 or in row 5. We're almost there. I mean, partly it's going to be about plumbing on the back end, and partly it's going to be with what we do with the outputs of these things. Well, I think you can almost hear it in the words. I want the circuit to come on when we're in this row or when we're in this row. It's an OR hookup between them. So just feed these guys, the outputs of these ANDs, into an OR gate. Now the other element we need to worry about is how to plumb the back ends of these. So let me do this for you. Look, this is kind of like a bus like on the back panel of a computer. So we're going to lead P down to here, Q down to here, and R down to here. And we want to hook P to that first line, Q to the second line, and R to the third line in that circuit. And same thing down here. P to the first line, Q to the second line, R to the third line. In circuit diagrams, that's the usual convention. If wires are just crossing over one another, then no connection is intended. You draw a little black dot when you mean that they have to be electrically joined. So anyway, that's the trick. That gives you a way to make a circuit that has this particular I/O table. If there were 5 ones in here, well then I'd have 5 recognizers and I'd OR all those things together. Actually, I'll point out that probably wouldn't be smart, because if there were 5 ones, what I could do instead is recognize the zeros and then put a knot on at the very end and fix everything up. But anyway, this kind of shape is called disjunctive normal form, this kind of circuit. Why? Because it looks like a bunch of ands, not P, ANDed with Q, ANDed with R, or together. The other one is, let's see, not P, and Q, and not R. So it's the OR of a bunch of ands. That's the disjunctive part, is that you're going to OR a bunch of things together. The other things are conjunctions, but it's the OR of ands. That's disjunctive normal form. There is a conjunctive normal form as well, which would be the AND of a bunch of ORs, but it's less frequently used. I thought it might be good to do one more example of building a digital logic circuit that has a particular I/O table. So I just erased the previous output, and let's randomly pick some things in here. How about a 1 in that position and these 2? Sound good? I mean, I'm just really kind of randomly choosing things. Not that that necessarily means anything, I just want to show you the generality of this method of using disjunctive normal form to find a circuit. So we are going to need to recognize 1, 0, 0. We'll also need to recognize 0, 1, 0, and 0, 0, 1. Oh look, that's by random chance, I think I just picked the ones that have a single 1 in them. So, well, looking at this first one, it's going to be P, ANDed with the negation of Q and the negation of R. So if we let P, Q, and R come in from here, I'm gonna push down a little bit, because I want there to be room to make a bus right here on the left-hand side, where we'll bring those values down to the other recognizers. But what we want for this first recognizer is to negate the lines on Q and R and leave P all as it was. Okay. I may have gone a little bit too far, because I'm going to have a tough time fitting the eventual OR gate on the end here, but we'll make do. So the other piece of this, pieces of this, are I need to get recognizers for rows 6 and 7 here. And what I like to do is just drop vertical lines from the variables P, Q, and R. May have to take these farther than I did the first couple. Bring them down to there. Our next recognizer needs to have, let's check it, it's this one, where we have this 1 in the output. So that's 0, 1, 0. That's a knot on the outer 2, and a constant, or the one in the middle goes straight in. So P with a knot on it, Q, nothing changed, and R is that line, yep, R with the negator on it. Feed those guys into an AND gate and put it forward. You know, the anal retentive part of me is starting to bug out now. I should have kept these AND gates lined up, so I'm just going to redraw that one so it's the same. What did I have for the knots on that one? That was this 4th row, right? So P went straight in, Q and R need to be negated before going into this inputs on the end. Okay. And lastly, we need to recognize row 7, 0, 0, 1. That's a knot on P, a knot on Q, and R unmodified. And then finally, we take those three recognizers and feed them all into an OR gate. And like with AND gates, if you want, you can make a kind of a big version where it has multiple inputs. So something like that. So our output would be on that line, and it's going to come on exactly when one of these recognizers fires, and then it's going to be 0 when in every other position. So, all right, so just a little philosophy, I guess, on the point of this disjunctive normal form and showing that we can create any arbitrary I/O table, or rather we can create a circuit that implements an arbitrary I/O table. It tells you that this system, where we have AND gates and OR gates and NOT gates, is complete. It can produce any circuit, or functionally any circuit. Now, is this the best way to do it? Probably not. There's an entire branch of computer science where people look at optimizing these kinds of diagrams. You have a big complicated circuit with lots of logic gates in it. You want to get it down to the point where you use the minimum number of transistors possible so that it takes up less space on the layout for your CPU. So that's something that we can do by translating this, which is well, I can write it for you. This is translates into a logical sentence. It's P and not Q and R is the first recognizer. And that's going to be ORed with a bunch of other recognizers. So we have OR. This one is not P, Q, not R. And that's ORed with, the last recognizer is not, and then unchanged. So not P and not Q and R. Well, it just fit. The thing is, you can maybe use the rules of logic to work on this and try to simplify it, and you may be able to get a circuit. I mean, you know, a logical expression which you can then translate back into a circuit that does a better job, that does it more efficiently. Finally, in this topic of logic circuits, there are two other types of gates that we won't use very much, but you should know about them because in certain versions of transistor logic, these are actually the ones that are easier to create. So people use the ones I'm speaking of in actual building real circuits. And the things are called NAND and NOR. So let's see. NAND as a gate is written like this. You draw an AND gate and you put an open circle at the end of it, and then the output feeds out of that. This is really the same thing as an AND gate followed by one of our negators. And in fact, you should think of that circle as really being the negator. This little triangle with a circle on it is sort of a one input do nothing operation. The circle is what really does the negating. And so this is negating. So when they say NAND, it really means not AND. In other words, if we have P and Q here, the thing that's on this output line is the negation of P and Q. And it needs parentheses to make sense of it. It's also how you would interpret that, but the NAND gate. Now, there's a single symbol for that. It's called the Sheffer stroke. So this can be represented as P stroke Q. And it's an interesting exercise to find that the stroke actually just that one operator is complete in the sense that the and, or, and not were complete before. The reason is really the stroke sort of involves both an and a not. So, you know, you're getting at least two things out of it, but it's possible to also implement an or and a nor via the stroke as well. So that's just a fun fact. You can just use nothing but NAND gates and build any logic you want. The other operand, again, these two are not things we're going to use much in the course, but I just want to, for completeness, show them to you, is NOR. It's drawn like an OR gate with one of those dots on the end or circles on the end. And yeah, it is the same thing as OR with a not after it. So NOR means, just notice I didn't close my quote, NOR means the not of the OR. It's, the thing on this line here would be the negation of P or Q. And there's a symbol for this operator. When you want to think of NOR as a single operation, it's a downward pointing arrow. It's called the Pierce arrow, which is kind of funny. I think there was a car at one time called the Pierce arrow. This is not that. Mostly I just wanted to go over these because there's a couple of questions in the homework that involve the Sheffer stroke P NAND Q and the Pierce arrow P NOR Q. You get to the point eventually where you just read that as NAND and this is NOR. Okay, so that brings us to the end of section 2.4. Next up we're going to look at 3.1. We're moving along.